Hi everyone, I'm Nasira Kari. I'm the head manager of the HeartSafe team. Let's talk about the reliable defibrillator. The purpose of this presentation is a scientific project being developed by our team. This project responds to a need in the medical field, specifically cardiology, which is designed to save lives. It's to create an automatic defibrillator vest. Today, there are nearly 50,000 deaths in France due to cardiovascular accidents. For this type of accident, the speed of the medical response has a crucial role in the survival chances of patients. In fact, the sooner the heart receives an electric shock, the patients have more chance of escape, and it estimated at 3,000 the number of the lives that could be saved each year in France. This population at greatest risk in cyclists who do physical activity in the country or mountains, thus increasing the response time in case of accident. So, in response to this need, the French Center of Heart Research had asked us to create a defibrillator vest. This vest is connected to the heart by two electrodes analyzing cardiac activity in real time. The defibrillator uses the information to send an electric shock when needed. The operation of this will be explained by my colleagues Mathieu Jaoul for the numeric part and Mathieu Lemoreau for the analog part.
Hi, I'm Matt, and today I will talk about how does our heart work. So during each heartbeat, an electrical signal can be recorded from electrodes placed on the patient's body. This electrical signal is due to the contraction of both ventricles of the heart that regulated blood circulation in order to supply our body in oxygen. This electrical signal is called an ECG, and each part of it matches with an activity of our heart or ventricle and the atria. The peak called R, like here, in the PQRST part of an ECG, is when our ECG beat, and it's this peak that we need to detect in order to see if the heart has disease. Now that you know the basic elements of the heart activity, let's talk about fibrillation, and more precisely with ventricular fibrillation. This is due to uncoordinated contraction of the cardiac muscle. In that case, it's a medical emergency. We need to defibrillate the patient. So we need to send current to the body in order to stop this uncoordinated heartbeat and go back to a normal beat. Therefore, first we have to analyze our ECG and then to make a decision if the patient needs to be defibrillated. In order to make a decision of the hypothetical fibrillation, we need to record the signal from the heart. This signal is very noisy, disturbed, and without a big amplitude, so we need to amplify it. Right after, we can begin the treatment of the ECG in order to see if we are in fibrillation or not, and so to make a decision. This has been done with this card, the STM32, and this card has sufficient power and a sufficient processor to make all the calculation we need and do also real time. Moreover, once we detected a heartbeat, we just power on a LED that just show the real time heartbeat, and if we detect a fibrillation, we just send the signal to activate the power part and power on another LED. So now I will just let Matthew continue to explain how the power part works.
Hi everyone, it's my turn to present you my contribution to the project. Naturally, I focus myself on the power part of the project. Why? Because my last year internship was in this part of the electronical engineering. I worked in a design office. We developed power suppliers for planes to provide them enough energy to fly. Moreover, I am used to develop these devices during my free time. For instance, I made some things to help my father or my uncle to be more efficient in their work. So now let's go back to the topic in hand. I'm here to talk to you about this thing. Actually, this board is not a full-scale defibrillator. This is a prototype at 1/10th scale. We choose to design a smaller model to preserve us and the future user to a high voltage shock. Instead to provide 1500 volts, this little defibrillator relays 150 volts. This preventive measure avoids us to be defibrillated by mistake. So now let's talk about the design. The input voltage is about 48 volt and should be increased until 150 volts, like I said previously. To reach this voltage, we use this little capacitor and diodes. And to store the energy for the shock, we use this big capacitor. When the order is given by the microcontroller, it is this part of the board, which come into play and delivers voltage in the right timing. As you can see, there is here a tiny wired sink connected to the board. This sink is a power resistor. It is used to establish the electrical model of the human body. We choose its value in agreement with the states of the art in medical papers. Normally, the impedance is around 600 ohm, but this defibrillator should equip a sportsman. In this case, the presence of sweat reduces the body impedance. That's why we use a 330 ohm power resistor. Maybe you're wondering what is about this wire. They are connected to our board and to the microcontroller to a small voltage supplier. In the final step of the design, we should design a box to join all parts of the project and to win the competition that we are in the next week.
To conclude, our team was able to create an innovative prototype defibrillator. This model works well and matches the specifications of both medical and electronic. Our team is proud to have accomplished this project and obtained conclusive results. This project was very stimulating, and teamwork has made us more efficient and develop our skills in management and cooperation. This will be very useful in our future professional activities. Thank you for your attention and see you for the next project, even more interesting. Bye-bye.